Hi everyone, welcome to Integral Calculus. Today we explore lesson 6.4, work in lifting object. Number one, the concept. In physics, work is the transfer of energy. Work is done by a force in moving an object a certain distance. A force can be thought as a push or a pull on an object. If force is constant, such as lifting a book, then work is force times distance, or W equal FD. And if force varies, such as pulling a chain to the top of the building, because we put more force near the stone, the chain is heavier, and less force near the end, the chain is lighter. In this case, we need to use calculus to compute work. Let's move on to number two. There are two units that we usually use, the US customary unit and the international unit. So let's take a look at each one. In the US customary unit, force is measured in pounds, and force is the weight of the object. And distance is measured in feet. Work is measured in foot-pound. In the international unit, force is measured in Newton. So Newton is kilogram times meter per second square. And that is why we have the formula. Force is mass multiplied to the gravitational acceleration, F equal mg. Distance is measured in meter. Work is measured in Newton meter or joule. Okay, let's get ready for some example. Our first example is how much work is done in lifting a 10-pound book 4 feet off the floor. Well, if you look at the force here, this is constant. The 10-pound book stay the same throughout the lifting. You see that force is constant. This means work is just force times distance. Force is 10 and distance is 40 foot-pound. Exercise 2. A 200-pound cable is 100 feet long and hangs vertically from the top of a tall building. How much work is required to lift the cable to the top of the building? In this problem, force varies because the weight of the cable is getting lighter as we lift it up. And because the force varies, we need to use calculus. Let's sketch a picture here. This is the top of the cable, and this is the bottom. Here comes the cable. 100-foot cable. Somewhere right here is the ground. And as you see, it doesn't matter where the ground is. We are lifting the cable, so we're going to focus on the cable. In order to compute the work in lifting the entire cable, we're going to take a look at the work in lifting a part of the cable. A sample. Work done in the sample is force times distance. The force here is the force on this sample Well, this sample here have a distance of dy if we use the y-axis. And it has a weight of 200 over 100. So this is the 200 over 100 dy. The distance here, well, the entire thing is 100 feet. That means we have to do a distance. We got to pull it up a distance of 100 minus y. If this from here to here is y. 100 minus y. So this is the work done to pull a sample. 2 times 100 minus y dy. To compute the work done on the entire cable, we're going to add the sample from 0 to 100. And the sum in is the integral. So work is the integral from 0 to 100 of the work done in pulling a sample cable. 2 times 100 minus y dy. And this gives us 2 times 100 y minus y squared over 2. Evaluate from 0 to 100. 2 multiply to 100 times 100 is 10,000. And 100 squared is 10,000 divided by 2 is 5,000. So we have 10,000 foot-pound. Example 3. A 60-foot long rope weighs at 2 pounds per foot and hangs over a building of 100 feet. Find the work done to pull up half of the rope. Similar to the previous problem, when we move up the rope, it gets lighter, so the force varies. Okay, let's take a look at the rope here. It's the top, and this would be the bottom. We know it's 50 feet long. We don't care about the ground because we're going to focus on the rope here. On the bottom of the rope, I'm going to let it be 0. Halfway is 30. Up top is 60. To pull up half of the rope, we got to pull the top half and also the bottom half. Okay, let's take a look at the sample. Top half here. The work done in pulling this sample is force times distance. Force is the weight 2 dy, because this sample has the length of dy, multiply to the distance. Well, this is y, so the distance in moving it is t minus y. And we have a 2 times t minus y dy. When we pull up half of the rope, the bottom half also move up. So that means we have to pull the bottom half also. And this sample has a length of dy. Sample, bottom, half. Work on this sample is force times distance, which is 2 dy The distance here is 30 because the entire bottom half get moved up by 30 feet. So each part get moved up by 30 feet. Stay dy. And ta-da! The work required to pull up half of the rope is work moving top half plus work moving bottom half. Work moving top half integral. Well, we only move from 30 to 60, so it's integral from 30 to 60 to 60 minus y dy. For the bottom half, we move from 0 to 30. So 0 to 30, 60 dy. Yay! Do the antiderivative. 60y minus y squared over 2, 30 to 60, plus 60y, 0 to 30. Do the substitution here. 2, 60 times 60 is 3600 minus 3600 over 2. And then we're going to minus sub in 30. So 60 times 30 is 1800 minus 30 times 30 is 900 over 2. 41 60 times 30 is 1800. Work out the arithmetic and we have 900 plus 1800, which give us 2700 foot-pound. Ta-da! One more. Example 4. A bucket that weighs 4 pounds and a rope of negligible weight are used to draw water from a well that is 80 feet deep. The bucket is filled with 40 pounds of water and is poured up at a rate of 2 feet per second. But the water is leaking out of a hole in the bucket at a rate of 0.2 pounds per second. Find the work done in pulling the bucket to the top of the well. This is the cool problem. Let's do a picture here. Here's the top and here's the bottom. And in the bottom here, we have a bucket. Draw this bucket. Water's leaking out at a rate of 0.2 pounds per second. And then the bucket is moving up at a rate of 2 feet per second. Okay. Here's 80 feet. So when we look at this problem, we got to do two things here. The first thing is we're gonna pour the bucket, and the second thing is we're gonna pour the leaking water. Work in pulling the bucket. First, work pulling leaking water. the work in pulling the bucket, well, you just have to move it up 80 feet. So that's this 4 times 80. 4 times distance. The work in pulling the leaking water. That is the different story though, because the level of water is different at each second. We say that the bucket is the y equal 2t feet above ground. And also the water is -4d minus 0.2 t pound. Losing water. Moreover, during the time interval dt, the bucket moves a distance dy. Example work would be work is force times distance. The force here is going to be the weight, so that is 4d minus 0.2 t, and the distance is dy, because during the time interval dt, the bucket moves a distance of dy. We need to do the substitution here, and then the sub is y equal to t, so that means t is y over 2. 4d minus 0.2 y over 2 dy. Or 4d minus y over 10. dy. Okay, got it. Now we can figure out the work pulling the leaking water, which is the integral from 0 to 80. It's got to pull it to the top of the well of the sample work. 4d minus y over 10 dy. There's 320 plus 40y minus y squared over 20 divided from 0 to 80. And we have 320 plus 40 times 80 is the 3200 minus 80 times 80 is 6400 divided by 20. And then when we sub in 0, we just have 0. Oh, how fortunate. So 320 plus, that is the 2880. And that gets us 3200 foot-pound. Thank you for watching. I hope you found the content useful. Please like and subscribe to help the channel grow. I will see you in the next video.